I'm really happy to tell you about some work that I've been doing in the last year together with my colleagues Alexandros Bampoulidis, Alessandro Bruni, Daniel Kales, Christian Rechberger and Walch. We came up with a solution that connects mobility data to infectious disease in a privacy-preserving way. Our approach is orthogonal to contact tracing apps. We only require feature phones and the data is already available by mobile network operators. Our solution gives a big picture of a current outbreak, but we cannot do contact tracing, so we cannot see individual infections. It is long known that human mobility is a critical factor in infectious disease for two reasons. First, for the increased contacts between susceptible and infected individuals. As a countermeasure, we have now these lockdowns. And second, for the introduction of pathogens into new geographical regions. This is a reason why we have this conference, not in Amsterdam, but online. To sum up, understanding the human mobility directly translates to a better understanding of the dynamic of a pandemic. 10 years ago, researchers started to connect mobile phone data to infectious disease. And the outcome you see on this slide is a prediction of future outbreaks of a particular disease. And this was verified with many more infectious diseases like dengue or cholera. So far, researchers aggregated mobility data of all subscribers of one mobile network operator. This worked quite well to get a general mobility pattern of the whole population. But they had to admit that they had issues when there are relatively few cases. So if you're at the beginning of an outbreak or at the beginning of a second wave. And they also had some problems when there were mass gatherings. So events where a lot of people come to one place. Our proposition is now to close this gap. And therefore we propose to aggregate only the mobility data of infected individuals. And this should lead to a more accurate picture about the current outbreak. But this seems rather obvious to do, so why wasn't this done so far? The reason is because of privacy issues. If you do not have a knowledge in cryptography, then you only have two options how you could connect the mobile phone data to infectious disease data. And the one is that the researchers send the patient's identifiers directly to the mobile operator, which then respond with the location data of these infected individuals. In this way, at the end, the mobile network operator learns who is sick and who is not sick. Clearly a thing we do not want to have. A second, maybe a bit better option with regards to privacy is if we would give researchers access to non-anonymized data records. So essentially they go to the premise of a mobile network operator and can then download the location data from infected individuals. But in this way the researchers would have access to all the location data of a mobile network operator. Still not good enough. And the solution is now cryptography. In particular, we are using three privacy-enhancing technologies. The first one is homomorphic encryption. Through this new encryption scheme, we protect the patient's identifiers. Second, we use zero-knowledge proof techniques to ensure that the cardinality of the identifier set has a certain minimum size. And because we already know that only aggregating over location data still leaves room for re-identification, we add noise to this final heat map and have this beautiful framework of differential privacy to get some mathematical guarantees out of it. Now let's look at the protocol. On the left you see the researchers that have the patient's identifiers, here depicted with their phone numbers. The first thing in the protocol is that the researchers encrypt these identifiers with homomorphic encryption. Then they can send it to the mobile operator, which has its own database of all his subscribers with associated location data. All the computation on the mobile network operator side happens in the homomorphic domain, so the patient's identifiers never get decrypted. The mobile network operator performs 3 steps. The first one is he validates the request. So he looks if the request is malicious, if the researchers are trying, for example, to single out somebody. More to that later. The second step is the heart of the protocol. So this is the data aggregation. Here we build, or the mobile network operator builds the heat map. And the last step is adding the noise to this heat map to make re-identification very unlikely. And remember, the result, the heat map, is still encrypted and cannot be read by the mobile network operator. He then sends this encrypted map back to the researchers, which with their decryption key can decrypt the map and see the result. Now we're going to look into more detail in these 3 steps. First, the data aggregation, the core of the protocol, where we build the heat map. And this is essentially a vector matrix multiplication. On the left you see the vector with the identities. A 1 means this individual is infected, a 0 means it is not. And then we have the so-called mobility matrix, where you see in the columns the cell towers, here 1, 2 and 3. And the numbers in there represent the time spent by example individual 1, individual 2 and individual 3 in those cell towers, in this area of this cell tower count. And the aggregation of the mobility data of all the infected people is then just this multiplication. And I've highlighted this here for the first cell tower, so we multiply this vector with this column. You see we count in the first and the last, because the individual number 2 is not infected, and we arrive at 2 plus 1 equals 3. And so on for all the cell towers. You can imagine that the dimensions of this matrix and vector get very huge if you look at whole countries or cities. Note, all those operations have to be performed with homomorphic encryption. Since this is very costly, we're looking for an algorithm that perfectly fits our homomorphic encryption scheme and the packing methods for our ciphertext. It turned out to be that the baby step giant step algorithm is the best fit for our protocol. Now let's have a look at the validation of the request. In a high level, we want to have that researchers that are malicious cannot get any information out of it. And it is not that easy to detect malicious researchers because they only send us an encrypted vector. So we have to look in this encrypted vector if the request was malicious or honest. And since we cannot look into the ciphertext, we use some techniques that are known from bulletproofs. On a higher level, we want to have a mask, so we want to add this mask to the result in the end. And this mask should be 0 if the researchers are honest, and it should be random if the researchers were malicious. Since we are always computing modulo some integer, this random answer doesn't give them any information. In a more detailed way, we are computing two masks. First, we ensure that the vector that the researchers are sending is binary, and second, that it has a certain amount of Hamming weight. Here it is W, and the two parties can agree which value this W should be. And then we combine those two masks to one mask. With more sophisticated methods, we were able to have a soundness of up to two With more sophisticated methods, we were able to have a statistical security of 2 to the minus 58, which is considered to be very secure. The last step of the mobile network operator is to add the noise to the outcome of the data aggregation, because data aggregation doesn't always translate to privacy, and since we are talking about very sensitive data, we have to have some mathematical guarantees in form of differential privacy. The noise is produced by a Laplace distribution, which is a very narrow distribution centered around zero, and of course it's symmetric. We have this privacy parameter epsilon. And the larger this epsilon, the less noise we add, and therefore the less privacy we have. There is no general way to find a good value of this epsilon, so we conducted our own privacy utility trade-offs. And we did this on a concrete data set that was public with geolocation information. And we simulated that some of these individuals are infected. And on the left upper corner you can see the original map without any noise. And then we add a lot of noise in the right upper corner. And you can see the problem here. We have hotspots that weren't there before, so the utility isn't there. And if you look at 0.2 and 0.4, you see that they are quite similar to the original map, but still there are some changes, and so we can argue with the data that in this cases re-identification is very unlikely, but the utility is still there. Since we are using a lot of new privacy enhancing technologies, we also did a lead analysis of our protocol. And we choose to do this with regards to the GDPR, so the EU privacy regulation, because it's considered to be very restrictive. And this multi-page analysis I want to break down for you into one slide. And the first argumentation for the patient's data is that if you encrypt data and you do not give away the decryption key, then this data can be considered anonymized. And once we have done this step, it is clear that under the GDPR, this isn't to be considered anymore as personal data, and that makes things a lot more easy. Second, we're talking about the mobility data, and we protect it by adding the noise, so the differential privacy framework, and because it is considered to be good practice in the GDPR, we also add orthogonal technical measures. For example, only limiting the number of queries or restricting the area. And therefore the risk of de-identification is highly unlikely. And that's what most of opinions of the GDPR see as enough. So far we have been seeing how the protocol works and that it is compatible with the GDPR. But usually these privacy enhancing technologies come with extreme overhead in performance. So is this even feasible or affordable for whole countries? And the answer is yes. It took us less than 2 hours, or equivalently $10 on AWS, to perform our protocol for small countries like Austria or big cities like Singapore and New York City. We achieved this by using a highly optimized C++ implementation using Microsoft's homomorphic encryption library C. The benchmarks were conducted on AWS with 96 threads, and we had around 1 GB of data communication. Since the protocol scales linearly in the dimension of the mobility matrix, it can also be done efficiently for larger countries. As a last point, I want to tell you about the security and privacy guarantees from our protocol. We have done a security proof, and I want to highlight the main results. So from the homomorphic encryption scheme, if this is secure, we directly get semi-honest security for our protocol. But then we ask, is semi-honest security enough for medical records and location data? And we do not think so. Therefore, we worked on our protocol and can in the end show that the medical records are protected, so they are private against malicious adversaries. So whatever the mobile network operator does, he cannot get out who is sick and who is not. And the location data is protected by this differential privacy against malicious researchers. So even if they deviate from the protocol, the researchers, they cannot single out persons or individuals that were infected. Even though this protocol is very specific, the idea of our work was to convey the following message: that even in times of crisis, where it is tempting to maybe temporarily lower data protection standards for purposes like big data analytics, there are technical methods to keep data protection standards high. And those technical methods are practical and available right now.